Welcome to this short video on concentrations. Let's unpack what a mixture really is. A solute is the minor guest, the solvent is the major host, and together they form a homogeneous solution. Concentration is a ratio that describes how crowded solute particles are within solvent space. As the diagram shows, too high or too low concentrations both cause problems, so chemistry often seeks a Goldilocks balance.
Molarity, written M equals moles per liter, is the bridge between the tiny atomic world and the macroscopic volumes we measure in the lab. Picture the circular workflow of weighing, dissolving, and filling a volumetric flask. It's the standard method. Remember that molarity shifts with temperature because liquid volumes change, so it's ideal for stoichiometry and titrations when conditions are controlled.
Molality and normality solve two different problems. Molality measures moles of solute per kilogram of solvent, so it stays stable with temperature changes and is preferred for thermodynamic effects like freezing point depression. Normality measures gram equivalent per liter and captures reactive capacity useful for acid-base chemistry. For example, 1 molar sulfuric acid equals 2 normal because it donates 2 protons. Percent composition gives an intuitive way to describe mixtures in everyday and industrial contexts. On the left, volume percentages show up in products like sanitizers, perfumes, or wine alcohol content, while on the right, mass volume and mass formats appear in medical IV solutions and solid mixtures like paint. Percentages make it easy to visualize and manufacture without atomic mass calculations. When solutes occur in trace amounts, we switch to ppm and ppb. Think of 1 part in 100, a million, or a billion. The visuals compare a drop in a bathtub to a drop in an Olympic pool to make that scale tangible. These tiny units are critical for toxicology and pollution monitoring, and even trace concentrations can have serious environmental or health impacts. Dilution is an efficient way to prepare working standards from concentrated stock solutions. You add solvent to reach the desired volume, conserving the moles of solute. The beaker sequence in the graphic illustrates this process, and the simple equation M1V1 equals M2V2 captures it mathematically. As a practical safety tip, always add acid to water to avoid exothermic splashes. Choosing the right concentration unit depends on context, as the decision framework shows. Use molarity for stoichiometric reactions, molality when temperature varies, normality for proton counting titrations, percent composition for consumer products and manufacturing, and ppm/ppb for trace detection and toxicity. Selecting the appropriate unit is the foundation of reliable experimental results.